This section examines crank angle sensing. Crank angle sensing uses information on the speed and position of the crankshaft to control ignition timing and injection sequencing. The control unit can then trigger the ignition and injection to suit operating conditions. The position sensor may be mounted externally on the crankcase wall, or it may be inside the housing of the ignition distributor. Inductive type sensors act as a small alternator and generate a sine wave, alternating current voltage. The teeth on the flywheel ring gear can be used to induce the voltage in the sensor, inducing 1 pulse per tooth. The frequency of the pulse allows the control unit to detect engine speed, or RPM. Crankshaft position is detected by a separate sensor, also an inductive type. It sends a signal to the control unit when a pin or bore passes and generates 1 pulse per revolution. It signals the control unit that the number 1 piston is, for example, 80 degrees before top dead center. Ignition timing is then decided according to the operating conditions and triggered to occur a certain number of degrees from that point. When only one sensor is used, the pulse inductor is shaped to provide information on both crankshaft speed and position. A disc attached to the crankshaft pulley has a number of equally spaced ribs around its circumference, but 2 ribs are omitted. The frequency of the pulse from each rib gives engine speed in RPM, but on each revolution, the pulse alters as the gap from the 2 missing ribs passes the sensor. This again gives the position of the number 1 piston. This section examines feedback and looping. During engine operation, the 3 pollutants enter the catalytic converter. How efficiently they are converted depends on the composition of the exhaust gases. And that depends on the air-fuel mixture sent into the cylinder for combustion. If the air-fuel ratio supplied to the engine is too rich, then the nitrogen oxides are converted efficiently, but the carbon monoxide and the hydrocarbons are not. If the air-fuel mixture supplied to the engine is too lean, the opposite occurs. Carbon monoxide and hydrocarbons in the exhaust gas are converted efficiently, but not the nitrogen oxides. Highly efficient conversions of all 3 pollutants occur only in a narrow range of air-fuel ratios. This range occurs around the ideal air-fuel ratio by mass of 14.7 parts of air to 1 part of fuel. This is called the stoichiometric point. It's also called the operating window of the 3-way catalytic converter. If the mixture ratio falls outside this range, the efficiency of conversion of either the nitrogen oxides or the hydrocarbons and carbon monoxide will rapidly decrease. Because of this strict requirement, vehicles with a 3-way catalytic converter have a feedback system called looping. The ECU monitors the air-fuel ratio by using an exhaust gas oxygen or EGO sensor, also known as a lambda sensor. This sensor obtains information about the composition of exhaust gases. It's located in the exhaust manifold and it's connected to the control unit. Closed loop can mean the control unit does receive feedback from the EGO sensor and acts on it to alter the injection setting. Open loop can mean there is feedback to the control unit, but it is ignored, and the fuel settings are then determined from the programmed memory. Alternatively, open loop means that there is no feedback to the control unit. In that case too, fuel settings are determined from the programmed memory. During cold starting, this sensor is at too low a temperature to provide an output voltage to the control unit, so it operates in open loop. The same applies until the sensor warms up. The control unit is in open loop. It is only when the EGO sensor reaches its operating temperature that a voltage corresponding to the air-fuel ratio is sent to the control unit. During normal operation, open loop may also occur during idle or under maximum power. It can also occur if there is a fault that causes the air-fuel ratio to be excessively rich for long periods. Similarly, for a fault that makes the ratio too lean for long periods. When the lambda sensor reaches its operating temperature, around 350 degrees, it sends an output voltage to the control unit to signal whether the mixture is richer or leaner than a lambda value of 1, that is, the air-fuel ratio of 14.7 to 1, also called the stoichiometric point. When the mixture deviates from this, the output voltage changes sharply. The voltage of the signal from the EGO sensor changes sharply when the air-fuel mixture changes from lean to rich. If the control unit sees the voltage as high, then the quantity of fuel injected is reduced. Similarly, if the mixture changes from rich to lean, if the voltage is low, more fuel is injected to enrich the mixture. The control unit then adjusts the pulse width of the injector accordingly to ensure the most efficient operation of the catalytic converter. During engine operation, this adjusting is continuous and almost instantaneous, trying to maintain an air-fuel ratio for lambda equal to 1. Hall effect sensors can also provide a voltage signal and, like the inductive type, can be mounted on the crankcase wall or inside the housing of the distributor. The sensor has a permanent magnet and a Hall switch as part of its assembly and an air gap between the magnet's north and south poles. The switch is on one pole of the magnet, and an interrupter ring with a number of square-shaped blades or segments rotates through the gap formed by the poles. When it's used in a distributor, this interrupter ring has the same number of blades as engine cylinders, and a corresponding number of windows or gaps between the blades. The magnetic field is strongest when the gap is aligned with the poles. This allows the switch to earth a low current signal voltage that is applied to it. When the interrupter ring rotates so that a blade is in line with the poles, the magnetic field is shielded and the signal voltage is not earthed. With continuous rotation, the blades repeatedly move in and out of the air gap, and the signal voltage will appear to turn on and off repeatedly. The control unit uses this on-off signal to detect engine RPM and to control ignition timing. If a sequential injection mode is used, the position of the camshaft must also be signalled to the control unit. This is done by making one blade of the interrupter ring shorter than the others. It's called a signature blade. It passes through the sensor and alters the signal, so that injection commences at the correct time in the cycle. Since the distributor rotates at camshaft speed, the sensor in the distributor provides camshaft position readily. When the sensors are on the crankshaft, a separate sensor is needed for camshaft position. It identifies when to commence injection for the number 1 cylinder. Injection for the other cylinders then occurs in the same sequence as the firing order. This section examines modes of fuel injection for petrol engines. A mode of injection describes the timing and the sequence of injecting fuel. Simultaneous injection means every injector opens at the same time. Fuel sprays into each intake port where it stays until the inlet valve opens. During each engine cycle, the injectors open twice, and each time they deliver half the fuel needs of each cylinder. This happens regardless of the position of the intake valve. The injectors are triggered by the ignition system. So for a 6-cylinder engine, the control unit triggers the injectors on every 3rd ignition pulse. Sequential injection means injection for each cylinder occurs once per engine cycle. It is timed to each individual cylinder in the firing order. Fuel spray stays in the intake port until the inlet valve opens. Grouped injection divides the injectors into two groups. A 6-cylinder engine can have injectors 1, 2 and 3 in Group 1 and injectors 4, 5 and 6 in Group 2. The control unit operates the groups in turn to spray fuel once per engine cycle. Group 1 injects, then 360 degrees or 1 crankshaft rotation later, so does Group 2. This happens regardless of the position of the intake valve. Just one injection provides the full quantity of fuel for each cylinder during that engine cycle. In some applications, different modes of injection are combined so that the mode changes according to the operating conditions. Sequential mode may be used for low engine speeds, changing to simultaneous mode at high speeds. The same principle is used in changing from light loads to heavy loads. Similarly, the mode may change from group injection to simultaneous. Using different modes for different operating conditions makes the most of how the fuel is used, and that improves power output, fuel economy and emission control. Crank angle position and engine RPM can be detected optically. A signal rotor plate is attached to the distributor shaft. It has 360 slits at 1 degree intervals on its outer edge. Inboard of the 1 degree slits are 4 slits, one for each cylinder. They provide the reference points for the ignition timing and the fuel injection. One is larger than the others to provide the signature effect for the number 1 cylinder. As the rotor plate turns, it passes between 2 sets of diodes, positioned in line with the slits. The diodes above the rotor plate are light-emitting diodes, while the ones below are photodiodes. When provided with a suitable voltage, light-emitting diodes transmit a fine beam of light. Photodiodes receive this light and use it to make a voltage output signal. When a slit is in alignment, the light beam passes through and a signal is transmitted to the control unit. When the slit is out of alignment, the light beam is interrupted and the signal falls to 0. The control unit uses the interruption of the light beam and the 1 degree slits to gauge engine RPM. It uses the interruption of the light beam and the signature slit to gauge the position of the number 1 piston. All of this data is used to keep close control of ignition timing and fuel injection. This section examines variable intake manifold systems. The air intake manifold for an EFI multi-point engine normally has long branches of equal length. The long branches increase the pulsing effect of the airflow in each pipe and help charge the cylinders. The more air drawn into the cylinder, the denser is the air-fuel mixture when the inlet valve closes. And it's this density of the air-fuel mixture that determines how much pressure develops in the cylinder during combustion and the level of thrust on the piston to turn the crankshaft. The characteristic torque curve of a naturally aspirated engine depends mainly on how the engine's mean pressure changes across the RPM band. The design of the inlet system largely determines the mass of air that can be drawn into a cylinder at a given engine speed. So that means the inlet system largely determines the engine's torque curve. In general, a long intake manifold produces high torque at lower engine RPM, and higher torque is obtained at higher engine RPM with a shorter intake manifold. Manifolds that respond to changes in engine load and speed by changing their effective length are called variable inertia or intake charging systems. They can have controlling valves operated by the engine management system, which can extend the primary type manifold into 2 or 3 stages. The primary section is made long and narrow for the low range of RPM. The secondary section is shorter and wider for the high range of RPM. This combination maintains a high-speed airflow in the system. The 3-stage manifold extends the torque curve so that the torque curves overlap each other as advantageously as possible.